So hi everyone. This is going to be a talk about internals from the V8 JavaScript engine that powers both Chrome and Node.js. And I have this funky title, and I want to explain something about it. So first, weak collections are weak set and weak map. And this word ephemeron is an important technical device that is the key ingredient for the implementation of weak maps in the engine. And I'm going to explain how it works and what it actually is. And private fields are related to this because you can use weak maps to emulate private fields, to polyfill private fields, if you don't have an implementation available. But before I can explain all this to you, I have to give you a 20,000 miles overview about how garbage collection works. And for this, I want to walk with you through this program. It's probably a little bit strange, but we are interested in what happens in the heap space when we execute it. So when the first line is run, an object is created in the heap with one property, ID, that has the value 1. And then this object is referenced by the variable a. I hope you can see the color. Oh, it's only very faintly visible, but there's an arrow going from A to this object. And when we continue execution, sorry, something's wrong. I'm sorry, I seem to have lost internet connection. Okay, let's start again with this slide. So if we execute the first line, then we create an object in the heap which has ID 1, and we bind it to the variable a. Now you can see the arrow. Great. And that means the variable from JavaScript is now referencing this object in the heap. If we execute the next line, same thing happens. We get a new object in the heap, and b is now referencing this object. What we also can do is we don't create a new variable, but we create a property on A with the name x that holds a new object. So we create the new object in the heap, and now there's a new property on the first object, and this property references the third object. And there's an important device that one needs to understand if one thinks about garbage collection, and that is the so-called root set. And the root set is the set of all objects in the heap that is currently directly referenced from JavaScript land. And in this case, object 1 and 2 are referenced directly from JavaScript because A and B are still in scope. And the root set can change, can evolve during the program execution. For example, here, B goes out of scope. And then B stops pointing to this object. It's not in the root set anymore, and this object becomes dead, and the garbage collection can clean it up. There are other ways how things can become dead. For example, if we override the last reference to an object in the heap, in this case we override the property x with undefined, then the object 3 becomes unreachable and is now also dead, and garbage collection could clean it up. So the garbage collector has to solve the problem of how to distinguish live and dead objects. And to do this, it starts from the root set, finds all the objects that are in the root set, says, okay, I know these objects have to be live because they are directly referenced. And then it traces through all the references between the objects, finds everything that is still reachable, and the rest of the objects is dead, and can be cleaned up. And then at this point, the garbage collector would probably go about and compact all the objects, move them to one side, but for simplicity, I'm not showing this here. So now I want to talk about an example with maps, ES6 maps, that doesn't really work. So think about a website that you have and you show a welcome screen on this website. And for some reason, you have this templates map where you store for each component you have on the website the template. So when this line is executed, you create the map in the heap, and it's in the root set because we have a global variable called templates that's holding it. Then you create the component, the welcome component. It's also in the root set because we have the welcome component variable. And then you say, well, the template for this component is stored in some welcome HTML, and we execute this line. So two things happen. First, the template is created, and let's assume, for the sake of the example, that it's a big template. It takes up a lot of space. And then it's associated in the map with the component. So the key, that's the thing on the left, points to the component, and the value, thing on the right, points to the template. Now the site has loaded, the user is interacting, he's happy about the welcome screen, but he clicks it away. So onWelcome close is executed, and you have foreseen this, and say, okay, we don't need the welcome component anymore, let's replace it with undefined. So now the welcome component isn't referenced anywhere anymore, except from the map. But what you would like to have is that the whole thing goes away, because after the website is loaded and the welcome component is closed, no one will ever use it again. So with the map, you have a problem here, because the map keeps this thing alive. And this problem can be solved with weak maps. So let's walk through this example again, but now with a weak map. So again, we create a weak map in the heap. It's referenced by the global templates, that's why it's in the root set. We create the component. And now we insert the template again. Template again is big, but now the entry in the weak map looks very different. There is a dashed line which shows us that the link from weak map to the component is weak. That means weak map references the component, but from the point of view of the garbage collector, it's not keeping the component alive. And the other arrow is blue because it also has a special function. It only keeps the template alive as long as the key is alive. So when sometime later the user closes the welcome screen and you set the component to undefined, no one references the component. But now the garbage collector knows that the link from the weak map is not supposed to hold the component alive, and it knows this component is dead, I can clean it up. But to do this, it needs to do something to the reference. We can't leave a reference to an object in the heap that has been cleaned up. So what the garbage collector will do for us, it will call remove on the weak map, and it will remove the entry. And this will also remove the strong pointer to the template that we had, and the template becomes dead as well, and the garbage collector can clean up both. So this is a contrived example I've come up with, but I was actually searching on GitHub to find usages of weak maps, and there are actually real-world JavaScript frameworks that use weak maps in their internals. So now let's look at what an ephemeron is. We have seen this entry in a map which has a key and a value, and the map keeps both of them alive. And the only way that an entry dies is if you remove it or if the map dies. In a weak map, the situation is different. Here, the key keeps the value alive. So this is what we call ephemeron semantics. The value is only live as long as the key is live. And this means ultimately an entry in a weak map can die if the weak map as a whole dies, or if the key of the entry dies. So now I can explain to you how weak maps and private class fields are related. And the slogan here is that weak maps can be used to polyfill private fields. So if you don't have an implementation of private fields, you can use weak maps to implement them. But first, why would you care about private fields at all? And apparently, it's a good idea to somehow prevent users from accessing the internals they shouldn't access. React at the moment does it like this. If you do code reviews, that's pretty effective. But of course, if you can get the language on your side to help you, it's even better. And private fields do that. So here is a class foo with a private field m. You have to declare the private field in the body of the class, and then you can basically use it like a property on the object, but only from within the class. And the special syntax is that all the private fields start with a hash. So I don't want to go into the details of explaining private fields here. What I'm interested in is the memory organization. And the memory organization for this foo object looks like an ordinary property. The private field just becomes a property on the object. That means whenever you create a foo object, there will be some space in the object that is reserved for this property, and it can point out to whatever you associate with it. And you can get a similar behavior when using weak maps. So here is the same class, foo, but now with weak maps. And the idea here is that this class is defined in a module, so m can only be accessed by the code snippet that you see here. It doesn't leak to the outside. And then we can emulate the private field by putting a pair into the weak map and using the foo object itself as a key. So how does this look in the heap? We have one weak map, which will store all the values for this private field for all the objects of class foo. And when we create an object of class foo, then there will be an entry which uses foo as a key and points to whatever we want to have in the private field. And we will maintain this side table for each object that is created for the class foo. Now note that it is critical that we use a weak map here, because if we did this with the normal map, then we would have this monster map that keeps all foo objects ever created alive. But since the weak map only keeps the value alive as long as the key is alive, it doesn't influence the lifetime of the foo objects. Okay, so here's the cheat sheet. This is the class with weak map. That is the class with private fields. And in the weak map thing, you do a put with this as a key, and the private field you can just use as a normal property, and the same goes for accessing. Again, this is the same behavior from the point of view of the GC, because the weak map does not keep the foo objects alive. So whenever you are in the situation that you have two different devices that give you an implementation that achieves almost the same things, you have to ask what are the trade-offs. If they have both have the same trade-off, then it's probably not interesting. But this is not the case here. So on the one hand, we have the side table, and on the other hand, we have the in-object private field. So when should you use what? So the weak map has certain use cases, small use cases, I would say, where the weak map can really bring an improvement. The first is if you have a class and you know that a very, very small fraction of this class will need an additional field, then it can be a good idea to use a weak map for this particular field that only a small fraction of the objects of a class will need. Also, an application area might be that you need a field in a class, but only for a very short time during their lifetime. And the rationale behind this is that the field will then not take up memory in each foo object, but you will only spend the memory for the objects that need it or in the short time amount where you need it. Another use case is that you have objects, but you cannot alter them because they are coming from a library. You don't know if you can set the property on them. In such use cases, you can use a weak map because the weak map approach keeps the original foo objects unchanged. On the other hand, once private fields become widely available, they should be the default choice when you want to associate private data. And again here, if you're thinking about this, the rationale should be, oh, I'm looking at my code, I'm having a benchmark that is slow, I'm trying to figure out what is wrong, oh, this is using too much memory, and then you go to weak maps. You don't start out with weak maps. A big plus for the private fields is that the property access for private fields works essentially like the normal JavaScript property access. And that means that years of optimizations have gone into it, and it's really, really fast. The property access through the weak map is not really a property access. It's a lookup in this hash map. And years of optimization have gone into it too, but the overhead of looking up something in a hash map will always be there, which means that weak maps are always a little bit slower. But again, think about what this slower means. If you're doing something 100 times, things don't matter. If you do it 10,000 or 100,000 times and you need to do it, then you might start thinking about these things. So if you want to know more about weak maps, we have an explainer article on our website. And with this, I want to come to weak refs, which is another device that you have at your disposal soon, because it's a stage 3 proposal. That means browsers are now trying to implement it, but it's not enabled anywhere yet. And weak refs are special objects that have just one field in them, which holds a value that it doesn't keep alive from the GC perspective. And weak refs are not containers. They can't hold more than one object. So here's an example of how a weak ref could be useful. First, we'll do it without weak ref and see what the problem is. Suppose you have this sum class which does something, and you want to attach an observer to it. And if you do this, then the ops field will point to an observer. But if at some point later during program execution, your observer dies, then some class will hold onto it, because this pointer will keep the observer alive. And depending on your design, but most likely this is not what you want. You probably want the observer to vanish once you're not holding it anymore. And weak refs can give you exactly this. And it's easy to use. You just wrap the reference in a weak ref, and then the heap layout looks like this. The property on some class will point to a weak ref, which then will hold weakly the observer. That means the GC knows if observer goes away, then I can just replace the value with undefined. And when you want to access this thing, then you have a special function on the weak ref, which is called deref, which is allowed to give you undefined if the object has been cleaned up. Note that this example is an example where you can't use weak map or weak set, because both of them are not iterable. So here's the interface for weak refs. You have a constructor where you can wrap a reference, and you have a deref operation, which gives you the reference that is stored in the weak ref or undefined if the object has been cleaned up in the meantime. There is some special behavior that is in the standard. And that says that if deref didn't give you undefined, so it gave you the object you stored in, then it will keep doing so until the current synchronous piece of JavaScript code ends. But the motivation to do this was from a semantics perspective. The JavaScript committee didn't want the semantics, whether deref returns undefined or defined, or the object you stored in it, to depend on whether a GC occurred in a certain time interval. So here's my recommendation. Don't rely on this special behavior, but if you want to use the reference stored in a weak ref, then create a new variable and read out the value with deref, and then check whether it's undefined or not. The only thing you then have to care about is that you limit the scope of here, the variable is called opt. Because if you make opt a global variable, then you will be holding on to the value which you just put in a weak ref so that it can be freed. Again, we have an article about weak references on our website. Okay, so now we are in the last section of the talk. And here I want to explain to you a performance problem which got me involved with weak maps. But before I can explain this performance problem to you, I have to explain to you what a generational garbage collector is. And a generational garbage collector relies on the generational hypothesis. And the sloppy way of formulating is that most objects will die young. In languages like JavaScript, when you have an on-click event in a web browser, you will create a lot of objects that vanish after a few hundred milliseconds. So that's what the generational hypothesis says. So looking at the heap space, and assuming that we sorted the heap space, we have some kind of way to group the old objects to one side and the young objects to the other side. The generational hypothesis says the likelihood to find an object that is dead among the young objects is much, much larger than finding a dead object among the old objects. And the idea now is that we can leverage this hypothesis by dividing the heap space into two generations, the young generation and the old generation. And if we now visit the young generation more often and the old generation less often, then we will do less garbage collection work in total, but we will still find most of the dead objects because most of the dead objects will be in the young generation. So here's a picture that illustrates this. In a non-generational GC, when you do 5 GCs, you spend 5 time units. In a generational GC, you could opt to do 4 young space GC and then a full heap space GC. This only costs you 2 time units, but by the generational hypothesis, you know that most of your dead objects will be in the young generation anyway. So you will find most of the dead objects, although you spend much less time GCing. Okay, so now that we understand how a generational garbage collector works, I can explain the problem of cross-generation references. So suppose you're doing a young space GC, and you see this object Y. You see no one pointing to it, and you think, I can clean it up. But what you don't know is that there is an object in old space that holds a reference to Y. And you wouldn't see this reference because you only searched for pointers to Y from the young generation. So clearly this doesn't work. This needs a special device. And there is such a special device which is called a remembered set. And this remembered set acts similarly to the root set, but only for the young generation. So the remembered set keeps certain objects alive in the young generation because there is still something in the old generation that is pointing to it. And with this remembered set, everything worked very well in V8 until weak maps showed up in the old generation. Because the key to the weak map could be in the young generation, and then we would insert something into the remembered set that keeps the key alive. But the remembered set didn't distinguish between weak links and strong links. And that led to a detrimental situation where we had huge weak maps in the old generation that kept a huge amount of keys in the young space alive that we could have cleaned up, but didn't know because the remembered set was missing the information. So this was basically the bug that got reported. And what I did then, I introduced another set, the old weak maps with young keys set, that now points to the weak maps in old generation that still have a young space key. And then I taught the young generation GC to also go through these weak maps and clean up young keys that aren't referenced anywhere else anymore. So here is a micro benchmark that exhibits this problem, We create a weak map, and then we run through a loop for n times, creating new objects in each iteration. And note that the object we create in one iteration will die in the next generation, because obj is the only thing keeping it alive. The weak map is a weak map and doesn't keep its key alive. And if you plot the performance with both logarithmic scales, logarithmic means if this line is going up, it's really, really bad. Then you see that at 100,000 objects, the old implementation got slower, and then somewhere between 1 and 10 million objects, things really went bad. And introducing this new set, the old weak maps with young keys set, improved the benchmark at the point of 8 million from 2 minutes to 2 seconds. Okay, so in summary, weakness allows you to hold a reference to an object without actually keeping the object alive. Weak maps and private field offer similar functionality, but with different performance trade-offs. And performance from the V8 implementation perspective is always difficult to get right. There are so many things you can create on the web. There might just be your use case that we didn't think about yet. So if something looks wrong, file a bug. And if you have a benchmark that is slow, but you think it should be fast, that's really, really helpful. Then we can do something. So thank you very much.